Am I audible?
Yes, you are audible.
So let us wait for 5 minutes and then we can start with the session when a few more people join. Okay, so is my screen visible to everybody?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Okay. Cool. So today we will continue with the week 9 content. So in the previous session, how many of you had attended the previous session? Okay, so a lot of things from week 9 would have been covered. So everybody is clear with that, right? So should I first do a quick revision of what we have till now in week 9, or should I continue forward with?
Ma'am, a quick revision would be good.
I think we can continue the revision of week 9. Also have doubt with the practice assignment. Because yesterday's session, though I was present, but I couldn't focus due to some work. So that's the reason.
Practice assignments also was saying that we try to discuss. Okay, just give me 1 second. What is the deadline for week 10? Practice assignments. Okay. Okay, if time permits, we can continue with the practice assignments also. Meanwhile, we can start with a quick revision of week 9. So, for those of you who were there in the session or who are clear with what was taught yesterday, so I want you to take the lead a little bit and start explaining what till now you feel are matrices. Why do we need to introduce matrices in order to go towards graphs? And then what are the applications that we can get from there? Some quick notations also. So, anybody? Okay, so first of all, till now everybody is clear till week 8, right? That is very important. So
Yes, ma'am.
basically,
Yes.
all the types of collections. If you notice, matrices is just an extension of lists, correct? In a way.
I think it's an extension of
Yes, ma'am.
dictionary,
More
right?
like a dictionary.
No, a graph is an extension of a dictionary, but when we talk about matrices, can't you think of them as just nested lists? I mean,
But I
in
think
the
matrix
very
also
beginning, you can think of it. In the
extension of
very
dictionary.
beginning, you can think of it, and then we move towards a matrix implementation. But if you think about, so again, these are two different contexts here. One is that in the view of our particular course, we use matrix as basically a two-dimensional table, and we want random access. That is very important for us, right? That we want to have random access. So that is why we use dictionaries. But in general, one thing that I mean, this can be considered a little bit separate from the direct syllabus that we are viewing here. In a real world setting, if you have matrices in terms of, if you try to implement matrices in terms of a programming language, it is often viewed as a list of a list. So that is also one way to look at matrices. But the very important thing is that in this collection, in this particular course, we are referring to matrix as using a dictionary basically. Why? The reason is that we want to support random access. So for those of you who are already aware of some programming languages, I would like to make this distinction clear that usually we see matrix as a list of lists. For example, one language is Python, right? So in Python, the most common way to represent a matrix is as a list of a list. But we don't have the ability to have random access memory on lists throughout all languages. So that is why a dictionary is needed because it stores key value pairs. Now, how do we do that? That is the next question. So, okay, till now we know how a list how a list keeps a sequence of values basically. And what is one very important property of lists? Anybody?
It can store any type of values.
Okay, and what I'm looking for is more in relation to why it is or isn't used in matrices.
Random access.
Indexing.
Somebody said random access, right? So indexing is one property of list. Again, I won't deny that. But one very important property of list is that it does not provide any random access. So that is what differentiates it from a dictionary. Correct? It just keeps a sequence of values. Whereas a dictionary, what does dictionary store?
Key and value pairs,
Key
which
and
will
value
allow
pairs.
the
And
random
does it
access.
support random access?
Yes.
Okay. And what is one property about keys that should be fulfilled?
Keys are unique.
Yeah, keys are unique. Okay, that is very important. So if I try to if I already have a particular key and I try to use that key again in order to uh, basically initialize something, what would happen?
It will change the value.
Exactly, it will override the current value of that key. So we won't have a separate key, it will just override that particular value of the key. Okay, now what is the need of a matrix, first of all?
For quick comparisons or arrangements, we can say, right?
To check relations between two elements.
Okay, all of those are correct implementations. So let me start writing also. Matrix represented using dictionaries for random access. What else was there? Second thing what we talked about was need some sort of, again, this is usually when I write in terms of notes here, right? This is a very naive kind of writing based on what you guys give me answers. And in order to view the actual well-defined definitions, you can refer to the slides. So the slides are very, so I'm following the structure of the slides today. The slides are very good in going through the difference comparisons between list, dictionary, and matrices. So make sure that you know the notation that has been implemented there. Okay, so let's say two things. Okay, the other thing might be that what was something else that you guys said?
To check the relation between two elements.
Okay, to check or compare the between two tables. That is also a way to write something. Anybody else? Okay, so now another property is that we would like random. So again, what is the structure of a matrix? Till now in list we had a structure that way everything is linear. We have some indices. In dictionary we had key value pairs. What is the structure of a matrix? How many dimensions does it cover, first of all?
N cross
2D.
N, that means square.
Sorry,
It's a
It's
2D.
a square matrix. 2D.
2D.
Relations.
What do we represent? Rows and columns?
Rows and columns.
Okay. Matrix can be thought of as a two-dimensional or rather a two-dimensional table, and it can be represented using M and N, basically rows and columns. But then again, it is up to us the kind of notation we want to give. The general notation for this particular course is M rows and N columns. Okay. We can have R rows, C columns, that is okay. Depending on the question, these things might change. Now, very important thing, because a lot of you said that during quiz 2 you had issues with notations, right? That okay, indices start from 1 or 0 or like that. So given in the slide, otherwise I maybe try to mention it from further questions where the indexing starts from. But in the given slides, it has been said that by convention, rows and columns are numbered from 0. So if suppose a particular matrix has m rows, then what will I be from?
0 to m minus 1.
Okay. And what about n? Sorry, I mean for the columns, how will I traverse, or rather J traverse?
0
Same
to n
here,
minus
can
1.
happen.
To n minus 1.
Yes. Okay. So this much is clear.
Yes.
Yes,
Okay.
ma'am.
So again, we move towards the dictionary representation, and in that, I would like to just since this is a quick revision, I won't just delve into what this particular procedure is doing. I'll just write it and then quickly explain in brief. Okay, so here we have that create matrix procedure, which is given to you in the slides itself. So very quickly, what is it doing? It is initializing a dictionary. We have I equal to 0, and then we are doing something in a while loop, that while I is less than rows. Why? Important thing to note here, it is less than, not less than, equal to. So this is where you make mistakes when you're trying to run a pseudocode. It is less than equal to, which again it maintains with what I was discussing just before this, right? Okay. So it is initializing a matrix I is equal to 0 while I is less than rows. Matrix I is initialized by again another dictionary. What is this called? What is this making?
It's making a nested dictionary.
Yes, exactly. It's making a nested dictionary. After making this nested dictionary, we again initialize j equal to 0. So what will j represent here?
Internal
Column.
key.
The columns. J again, yes, j is a key also, but again a variable. J is a variable that keeps changing, and then we use that to assign values to that particular key. And mat ij equal to 0. Why are we doing mat ij equal to 0 here?
So rows cross columns, so I is row and J is column.
Yes. So basically, mat ij refers to one particular element of the ith row and the jth column. Okay.
Okay, man.
And why are we initializing it with 0 here?
We are making a zero matrix actually. But
Yes. So we are making a 0 matrix basically. So we are initializing everything with 0 because right now we are assuming there is no relation. Otherwise, we could have initialized it with some other logic also. That okay, if some condition holds, then make it 1. If otherwise, make it 0. If you would have seen some examples using graph also, right, in the previous session itself.
yes, ma'am.
So depending on some logic, we initialize it to something else. But by default, when we create a new matrix, a raw matrix, given the rows and columns, we try to initialize a 0 matrix with with a rows number of rows and columns number of columns. Okay. So that was about creating a matrix. Now, let's say we already have a matrix. For example, we just have a nested dictionary. So it is very easy for us to then process that particular matrix or dictionary, right? Again, very easy. This is again the notation which is there in the slides itself. So given that my matrix is some matrix, so let's say from here we created a my matrix is equal to create matrix. How many rows and columns? Let's say 3 by 3. 3 rows and 3 columns. So what will I and j be here? What will be the value of I and j?
Both are 3.
Possible values of I and j.
0, 1, 2.
0, 1 and 2. Okay, so possible values of I and j here are 0, 1 and 2 based on this pseudo code. Now we move towards processing something. So now we already have a matrix, and what will be the structure of this matrix? Let's say I have 0 values. So would anybody like to tell me what this matrix would look like?
Square matrix.
This is
How
a
would it look like?
by
It's a
3
nested
by
dictionary, right?
3 by 3 matrix, no?
Yes, 3 by 3 matrix.
Again, 0 of 0 inside. 3.
Then
1 of 0.
0, 1, 1 of 0.
2 of 0.
okay. Same thing
And
again.
outside 1. Yeah, the same.
Same thing again for 1. Same thing again for clear. This is how this particular my matrix is represented. Now, in order to do something with this, all the values are 0 here, right? All the keys are 0, 1, and 2, which is I and j. For each row I of my matrix, how will that particular thing render? So basically, which 0, 1, and 2 here will refer to the first line for each row I of my matrix. Anybody? Would it be these 3? Or would it be these 3?
Yes, ma'am.
Yes, for which one?
It can be anything.
It can be anything. Why? So we have a dictionary in this format.
Ma'am, can you repeat the question?
So I'm saying that the very first line, right? For each row I of my matrix, we have so many 0, 1, and 2s here, right? Considering that, okay, the values are 0, 0, 0, we have so many i's and j's filled here. So
Yes.
for each row I of my matrix, which out of these numbers in this particular matrix represents
The outer dictionary.
yes, the outer dictionary, right? These 0, 1, and 2.
ma'am.
Yes. So these 3 represent the row I. And once we enter this particular one, let's say the first one will be for each row I of my matrix. I is 0. After I is 0, J will be represented using this inner matrix. For each column J, we will traverse through this 0, this 1, and then this 2. And then we will do something with my matrix Ij. So in the very first iteration of I, we will be working with only this much and changing these values. This 0, this 0, and this 0. Second one, we will be working with this. Third one, we will be working with this. So this is very important distinction, because once this is not on your tips, you will take a lot of time to solve the questions, and that will eat up a lot of time, especially in the end term. So I would recommend you to practice a lot and be aware of how exactly the processing is happening, so that you see the code and you are able to directly implement it rather than just running it again and again in your mind. Okay.
Ma'am, I have one question.
Yes.
Can you please explain about this zero rows, meaning from where it starts?
So it starts from here. So in first iteration, so here, okay. So this is how row and columns change. Okay. Firstly, row is 0, or rather, okay. Here I'll try to explain this.
And if you draw a simple matrix, it can be clear, I think so.
Yeah, that's how I mean, not exactly a matrix. I will show you every time what for each, what is the value of I and j for every for each. Okay, so we have row here, we have column here. Okay. For the very first iteration, the value of row will be 0, right?
Okay.
So for each row I of my matrix, when we talk about for each row, it is basically referring to the keys of, this is referring to the my matrix. So what are keys of my matrix? A list?
0, 1, and
Exactly. It's a list. What is that list? 0, 1, and
1,
2.
2.
So the very first thing that is happening here is for each row of my matrix, for each row I of my matrix, we are simply doing for each in this particular list. That is all.
Okay. So
Now,
by default, it starts from 0, the first row.
yeah, by that notation has been given in your slides, that we assume that it starts from 0.
Okay. Yeah.
So row
Thank you.
starts from 0. Now coming back to for each column j of my matrix, column value here would be
1.
no. Why would it be 1?
Column also start from 0, na indexing, na?
Yes, column also starts from 0.
From 0.
So here we are referring to this particular thing. Okay. So it can be considered as basically when we refer to keys, keys of my matrix I. These are keys of my matrix of I. So my matrix of I is what? This particular thing.
Yeah.
Again, another dictionary, right? So my matrix of I is this dictionary. Now the keys of this dictionary is again 0, 1, and 2. So now it refers to this particular 0 here. Then in the second iteration, what would the value of rows and columns be?
1, 0.
1, 0.
Why
Madam,
1, 0?
Madam, my matrix I refers to 0, 1, 2, na?
Yes.
Acha, keys of my matrix I. That means, acha, the inner dictionary
Yes.
you are referring to.
Yes, exactly. The inner dictionary I'm referring to. So
Okay.
now what will happen is for the second iteration. So again, it is a nested iteration. We have already gone through nested iteration so many times, so this should be clear by now. But just to revise once again, so that it is clear for the remaining session and you don't get confused in the little notations. For each row I of matrix, first we fix this I, we get inside the inner loop, we implement that inner loop completely for that value of I. So row will remain 0 and column will change from 0, 1, and then 2. Everybody's clear with this part?
Yes, ma'am.
Then row will become 1. Why? Because we don't have any other I. Sorry, we don't have any other column for row 0.
Excuse me, ma'am.
Yes.
Here R1 is 0 and now we are taking R2 as 1.
Yes. The second row starts with 1 index. So now we will have 1, 0. Okay. Then after that we will have 1, 1. 1, 1 is basically, if you think of it as a matrix, right? 1, 1 is a middle element here. So again, to write it in the form of a matrix, sure how good it will be. So this is a matrix, right? In maths, this is 0, 0, or let me just wait. This is 0, 0. This is 0, or is it the other way around? Who will specify this? Am I writing it correctly?
Yes. 0, 2.
Sorry.
Yes,
Should
it's
it be
correct.
this or the transpose of this?
It's the correct one, right?
Okay. So one will refer to the middle element. This is 1, 2. So basically, this is one row. 0, 0, 0, 1, 0, 2. So for row 0, we are changing the columns from 0, 1 and 2. So this is one row, the top 3. Then we have this. Then we have this. Then again, it will go on for 2, 0, and then so on. Okay. So it will basically be, here it will be 2, 0, 2, 1, 2, okay. This is a matrix representation of this nested list. This is how the rows and columns are changing throughout each iteration. And then we do something with my matrix ij. So ij representation is here. When we talk about my matrix ij, it will first do something with 0, 0, 0, 1, 0, 2, and then so on and so forth. So this is the order which we traverse in. Okay. Got it?
Yeah.
Okay. Let me just also show this one. This is the order basically. If you go this way, right? This, then you have this, and then you have this. This is the order of traversal. It's a little messy, so please bear with me for that. Okay, so this is the order in which we process elements. Typically, again, this is for this particular pseudocode. Don't think of this as something very universal. If suppose in our code we try to change something in terms of representation, let's say we do through columns first, rows later, then things might change. Okay, got it?
Yes, ma'am.
So
Ma'am,
please, yes.
in the pseudocode, we have to return keys of D, I think so. Why? Because it's a dictionary. There should be
We
some
have
change in
to
it.
return keys of. When we say return mat, we are returning the whole matrix, right? So this is
No,
what.
no, in this code. In the right, on the
Okay.
right side, for each, you have to change something, I think so.
For each row I of my matrix. Yeah. So basically, we will have to increment I and j, and then we'll need to do some computation. That is definitely there. So we will just like here while creating, we were, but rather, no, for each implementation by default doesn't use implementation, right? When we are doing for each and when that implementation will complete, it will directly go back and increment the I, right?
But we have to write for each keys in the key list, I think so. Keys of D or something.
That it depends again. It's a pseudocode, right? This is not a proper code in which we are writing in a language that is very rigid. It depends on us how we are representing it. If we want, we can have a complex representation. If we want, we can have a simpler representation. This is exactly what has been given in your slides. So it's just to show you that, okay, this is basically how we are, not that keys matrix part, that is what I used to explain. But this green part is what it is showing, that how we process a simple two-dimensional matrix. Got it?
Yes,
So
ma'am.
again, I understand your point here that when you think of exactly what we are traversing, instead of just writing row I here, which is still a little bit ambiguous and more with respect to how we are defining that matrix, an easier thing would have been to just say for each in keys of my matrix, right? Just like we do in a list. And then
Yes.
again in the second one, it would have been this. That is why I have written this notation so that you intuitively understand exactly what we are iterating through in terms of a list. Because for each is typically used for a list, right? In terms of a dictionary, again, also we can use for each. I'll have to check the notation on this one. Not so sure about that. But typically, in this term, these are lists. These are not dictionaries. These are list data structures in which we have stored 0, 1, and 2. And then for each my matrix, we have for each my matrix of that particular row, again we have 0, 1, and 2. So now for this particular notation, we can have two representations of pseudocode. One is using keys of my matrix. One is a very simpler one. Very intuitively, we go that okay, row I, column J, and do something with ij. So first row, so the ith row, jth column, we do something with that element. So this is a much more intuitive representation for a pseudocode. That is why it's pseudocode, right? It's not the actual code. In a proper implementation in a language, we can't write just for each row I of my matrix. My matrix would have been either a nested list or a nested dictionary of some sort, right? So in such a setting, we would require a proper notation, which you are referring to.
So, madam,
Again.
these kind of generally we start with from 0, but means we can explicitly make it 1 or 2 or any number.
Yeah, we can. It depends on us. So this basically this representation comes from this representation, right?
Yeah, correct.
So we are initializing I to 1. If I initialize I to 100 here, it will be 100, 101, 102. If I initialize J to, let's say, some other 50 arbitrary number, then again, it will change the notation. So this is for ease of understanding and for, I would say, universality here that, okay, since we'll be using this in a lot of questions, rather than create confusion regarding ing can be whatever, let's stick to 0, 1, and 2 so that things are uniform.
So in our syllabus, madam, this up to 2-dimensional is there, no? The 3-dimensional is not in our syllabus. Right?
I will have to check that once, but yeah, as far as I know, it's not there. So based on what I can see, it's usually one-dimensional.
2-dimensional.
But I will have to check because we have graph notations also, right? So one thing is matrix, other thing is graph. So we are introducing matrix in order to move towards graph. So I will have to once check the later content. So yeah, I'll let you know by the next session.
Hello, ma'am.
Yes.
Ma'am, I have a question. In this
Mhm.
nested loop, for each row, we are seeing the each column of that row. So here 0, 0, 1, 0, and 2, 0. So how it is represented? Because in this matrix you have written that 0, 0, 0, 1. So I'm not getting this.
So in this, so you have gone through matrices in maths, right? Have you
Yes,
taken
ma'am.
maths?
Yes.
So in maths, you would have gone through the notation of matrices. So how do we represent matrices? Firstly, it's two-dimensional.
Yes.
And then we have something called I comma j written here in matrices.
Yes,
Correct?
ma'am.
So that ij refers to the basically the position of that particular element in that matrix, right?
Yes, yes,
And
ma'am.
in
Yes.
this case, ij refers to the row, or in general also in matrices, ij refers to the ith row and the jth column of that matrix. So here when I say 1, 1 here, right, in the middle, let's say I'm referring to the middle element here, which is 1, 1. I am referring to the second column and the second row.
Second row.
Yeah, so it is this particular element here, this.
Yes.
So if you talk about the loop, then in the internal loop, it is the second one, and in the external loop, also it is the second one. So overall, it will be the fifth iteration in this for each, which will be running. And these represent the value of I comma j, which I'm writing. It is not the actual value of what is there in the matrix.
Okay, and then in this nested iteration, how it is represented?
represent it as in, this is what we are doing, right? Do something with my matrix I comma j. So this is how we will write my matrix 0 comma 0 will do something with the first element. My matrix 1 comma 1 will do something with the middle element. My matrix 1 comma 2 will do something with this element.
Okay. Okay, ma'am.
Okay.
Yes, ma'am.
Now, iterating through the rows again, some things have already been written. So this was more intuitive, like somebody pointed out, right? That this is we have to use keys of my matrix and keys of my matrix I. So in the future slides, so such notations are also there. I would urge you to once go through them on your own, because I've already introduced those conceptually to you. So yes, okay. So it
Okay,
has
ma'am.
also been mentioned that to improve readability, we just use columns and rows, but they have also shown the sorted keys matrix notation also. So if you directly get rows and columns in the exam, it's because it's already mentioned in the slides what they represent. Okay. I would urge all of you. So a lot of you, I might have some doubts with notations and everything. I would urge all of you to once go through the slides at least. So a lot of lectures, sorry, a lot of weeks have very few slides. It's in the beginning there were a lot of slides in each week, but for the later weeks, at least what I see in week 9, there are only 2 slides. Week 10 also, I think, yeah, two slides. So in most of the classes, or rather in most of the videos, the live the lecture videos that are there, the professors are just talking and building up intuition, right? So at the end, it boils down to just 1 or 2 slides, which are the actual content of notation and how things are working, how what the pseudocode is there. It is not that difficult to go through them. Every week, I expect that you go through them once at least, so that your notations and how things are represented are clear. It will help you approach some questions also if you know exactly what is happening in the pseudocode that is written in this particular slides. And specifically for activity question, I don't know how many of you are doing activity questions yet, but specifically for activity questions, it is very important that you go through whatever slides are there, because a lot of activity questions are directly in reference to the videos and not independent questions. So you would require the slides for that also.
Okay, ma'am.
Okay, so that is all for the basics of matrices. So again, this was just a sort of revision. So I hope now it is clear to everybody. Even if now you have doubts, please ask right now, because after this, in the next session, again, this thing won't be discussed again and again, right? So now I hope everybody is clear enough to move towards graphs. I would like to at least
Yes,
touch
ma'am.
upon
Clear.
all the concepts which are there in the basically the lecture slides at least, and then you can go through the video content on your own for the examples which have been shared.
So what are you trying to say is, like first you enter the first row, take all
Yeah,
the
so first I
columns,
enter the first row. Yes,
uh,
then I iterate through all the columns in
all
that
the
particular row.
columns till you finish the columns. Then you
Yes,
move to the second row.
yes.
That is the gist of the discussion.
Not just that, that is one part of what we discussed. The other is how the pseudocode is represented, exactly how we are iterating, uh, the representation of a nested dictionary, why in this particular row is keys of my matrix, why this is keys matrix I, why we will rather be using rows and columns, and how to create a matrix. So all this is discussed. Why we need a matrix,
So
basically.
for each row I for matrix,
Hmm.
keys my matrix. So basically, keys my matrix will represent the row only, the 0, 1, 2.
Yeah, keys of my matrix will be the outer. So this is a nested dictionary. My matrix is a nested dictionary. When I say
Hmm.
keys of my matrix, the outermost dictionary, whatever keys it has, it will return in the form of a list. And what does that represent here? If you go back to this, the outer dictionary is this mat. and mat is being filled with empty dictionaries for each I. And what is
Okay.
that each I? A row. So that is row representation. The outer dictionary
Mm.
represents rows. The inner nested dictionary represents the column of that particular row.
Okay.
And again, we don't need to stop here. This is just the 2D representation. For each column also we can have a next 3D kind of a
Yeah.
representation. But that is a
Mm.
little bit more complex. We won't go much into that to avoid confusion, at least for now. So this is the notation that we'll be moving forward for matrices at least. Now using matrices, we come to the concept of graphs. So I think graphs were also discussed in the last session. So who will help me just go through graphs once? Who will take up the initiative and explain why we need graphs and how we represent graphs? Anybody?
Graphs are also represented in the same manner, right?
We have one more notation for graphs also, but yeah, more or less we can say that is the notion of introducing matrices. So we can show the graphs in terms of adjacency matrix and adjacency lists also in some cases. But what I'm looking
Yeah,
for
if
is more of
there's a
a
presence of edge,
representation of
then
using that vertices and edges.
Graphs are basically, madam, with nodes and edges, directionless or with direction.
Okay. So
How the
what
nodes
are
work.
nodes?
Nodes are basically independent. We can say independent
which are not
variable.
having the edge actually.
So,
Sorry.
two independent. Suppose there is a graph of three nodes. So three
Uh,
nodes can we assume as a three independent variable. So, uh, so, so if the three independent variable are connected, that means there is some relations. And if it is a
okay.
directional graph, and so if one is directed to two, that means graph one is connected to two, and so two depend on one. And if two is directed to three, that means three depend on two. So direction and this thing is kind of.
Okay.
And that
So it's
relation is
not
known as edge.
that relation is known as edge. Okay. So again, it's not wrong entirely. More or less, it's the correct representation. It's just that the little things, right? That do they have to be independent? What do they signify? What is the need of graphs? Those are things that are still missing a little bit. But again, very good grasp of what graphs are. So just to reiterate once, when we move towards a graph data structure, it basically shows a relationship between two students. Sorry, not, I mean, given the example that we are using. So if you look at the slides which are there, which are given for this, right? Are you able to see that particular screen? Okay, I think I won't be sharing the tab. Till now, you were not able to see the window itself. Okay. Just give me 1 second, guys.
Yes, now we can see the slides.
Yeah, coming back to the slides. You're able to hear me, right?
Yes, ma'am.
Yeah.
So till now also I think I had shared the tab instead of the window. So I was also going through this particular one. So again, hoping that you have seen it. When I was referring to you, right, that you need to go through these ones, I was showing that okay, these are there two lectures which are there. Again, this notation versus rows and columns notation which they have represented, processing matrices, and this was the summary that I was referring to. So I hope that part is clear. So here also the student example is very important. So I thought you were answering with respect to this. So this is one example of how we are using a particular graph. So create mentor graph marks again. What is happening here? We represent it as a matrix in a pseudocode sense. But when we have been given a particular, let's say, different vertices or edges, then the representation is bound to change just a little bit, but that is just notation. At the end, when we talk about the pseudocode, we have uh, this matrix representation, first of all, where a graph is represented as an n by n matrix if there is an edge between two nodes. Nodes here are what? Rows and columns. So what I was, you said they were independent entities. That is correct in some way. But what I was looking for here is that those particular nodes are the, let's say, some ith column, some ith row and jth column that we are referring to. So that is one node, one I comma j in that Excalibur representation, right? One I comma j is the node, and whether that node is, let's say, 1 or 0, or if suppose it's a weighted graph, then it can be something greater than 1 also. If it is 1 comma 0 in this case, then it is a, there is an edge between that particular uh, that I and j. Got it? So here rows and columns are meant to represent two different entities, like you said. So I will let's say be student 1, j will let's say be student 2. Okay, and if student 1 and student 2 know each other, then the edge is 1. If they don't know each other, then the edge is 0. Let's say this is my problem statement that I have taken up. Or if two people are friends, then the edge is 1, otherwise the edge is 0. In that case, that relation is between I and j. So I and j are the nodes here. Got it?
Yes, ma'am.
Okay. So these are examples. I think they have in the last session we would have already maybe gone through the examples or some sort of representation of how things are moving here. So I won't go too much into this particular part. Moving to the okay, this is another problem statement. So in a lot of cases here, right, we are given a dictionary with marks for each subject. So what will be the format of this particular dictionary? We have read marks for mathematics. So what is read marks doing?
It's just naming the key as the number and the marks as the values.
Okay, key as the number and marks as the values. The number is what? The number is the
The card
representation of the
number, the
student.
card serial number.
Yes, exactly. The card serial number. So read marks is doing that. So math marks is basically reading the marks for mathematics, physics, and chemistry are also given. Now we have to create a similarity graph. What is a similarity graph? So in this case, we have defined the criteria for similarity, that two students are similar if they have similar marks in all subjects. And what does similar mean? The difference is within 10 marks, and this is for all subjects. So one practical example of this, okay, why we would need graphs in one case would be that let's say we have two group students. So we are making revision batches and we are grouping students in, let's say, 3 or 4 categories. That okay, these are, let's say, the ones who are we can say weak in some particular subject, or somebody who is doing good in some subjects, not good in some other subjects, or somebody who is doing well in all subjects, somebody who is doing exceptionally well in all subjects. So we want to create revision groups for such people. Again, everybody will have different problem statements that will be discussed. Somebody who is getting 90 plus marks, we will not discuss the exact same problems with them as somebody who is getting less than, let's say, 30 marks, right? The 30 mark student will have a different teaching approach, 90 plus will have a different teaching approach. So we need to segregate different students in different batches in order to optimize our teaching techniques, correct? How to do that? That is one way where we can use this particular notation also, that we have to, using the graphs, we can find the basically relationship between the different students and then figure out how many of them are similar to each other, and then we can cluster them into separate groups. So in this, the definition of a student being similar is that there should be a difference within 10 marks, and then once we segregate those into similar students, then we can have then we can basically assign that, okay, what kind of batch that is, what kind of approach we need to have for that batch. So here we are basically creating a graph for students who are similar, and now similar can be in both directions, right? If the difference you are saying in marks is 10, then in that particular two nodes will be connected. So again, once again revising, what is node representing here?
A particular element, you can say, right?
That is it. That is in general. With respect to this procedure that I am discussing, what
A
does a node
student.
represent here?
A
Yes, a
student.
student. A node represents a student. And what does an edge between a node represent?
They both are similar or not.
And the definition of similar is whether the difference in all subjects is within 10 marks. So this is what we are testing here. That absolute marks in all three of them should be less than
Less than
10.
10.
Only then we are giving this notation of 1. So what is actually changing the particular graph is only this one line. All the rest is the logic. In general also you will see mostly all the rest is the logic that we will need to define whether those two nodes have a connection or not, and then this is simply representing that what that connection is. In this case it is just a presence or not, so flag is 0 or 1. Otherwise we could have something more. Let's say we are calculating distances between two cities. In that case, similarity graph between I and j would be the distance instead of 1 and 0. Okay,
Yes, ma'am.
got it? So in the future I think you will see some TSP problem also traveling,
If you can
say from
reiterate this particular thing,
which one exactly?
like how you're approaching this one, the concept.
So here we are creating a similarity graph and we have defined some notion of similarity. The notion of similarity here is that in all three subjects, the difference of marks between those students should be within 10. So let's say I got 90% score for one particular student, and for another student I have score of 85 with me. Then the difference is 5. Now let's say in chemistry that same student who got 90
Come
has,
again.
okay, consider two students, okay, their
Okay.
maths marks are, let's say, 90 and 85. Their physics
Okay.
marks are, let's say, 30 and 39, and their chemistry marks are, let's say, 50 and 56 or something. Then the difference between the marks for each subject for both of those students is less than 10.
Yes.
So we define them to be similar students. That is the only criteria we are using to define the similar student.
Okay.
And now if the student is similar, we want to establish a connection between them in terms of a graph.
Hmm.
If they are not similar, in that case we want it to be 0, which is the actual initialization. So create matrix would have initialized everything to 0. Got it?
Okay. Okay.
And now what are we passing to this similarity graph function procedure? We have marks in all three subjects,
Hmm.
right? And marks 1, marks 2, marks 3 is basically got, we get that from this particular dictionary where we have the maths marks, physics
Where
marks,
I'm
and chemistry
actually
marks.
getting confused is,
Okay.
suppose you have, I got the point. I got the notion, like if they are similar, they are considered as similar student. But how you would relate the if like maths, physics, chemistry separately?
That is dependent on our problem statement, right? Here we don't care about whether they are performing good in maths and whether they are performing bad in chemistry, so we can't do them. So similar student basically means they have the same pattern, that both of them are good in maths to some extent, both of them are bad in chemistry. That is one
Suppose
set of students.
sequence number 5 and sequence number 10, they are
Hmm.
a similar student.
Hmm.
Then how would you represent them?
We would have one particular edge between row 5 and row 10. So the value of node, so basically node for that
Okay,
particular student
so
5.
I am thinking of a matrix from 0 to 29 row and 0
uh
to 29 column.
yes,
And if there is an edge, we represent it with 1. If there is not
Yes.
an edge, we represent 0.
Yes.
Okay, got it. Thank you.
Okay. So go through the pseudocode once more, all of you, and see what is happening here. This is basically the assignment that is happening in that particular graph. This is the logic that we have defined for us ourselves. That okay, this is if this holds, then they are similar. Okay.
Excuse me, ma'am.
Yes.
In the above pseudocode, the parameters are the dictionaries, right?
In this particular one, we have marks 1, marks 2, and marks 3. Dictionaries are math marks, physics marks, chem marks. So here, technically, if you see how we have keys of marks 1, so it is some dictionary, but I will have to check once if it's the exact same dictionary or not. Whether marks 1, marks. So basically, we have written the procedure here. So yes, these are dictionaries, but what is being passed here, that code is, I don't see that code here. So whether if they are passing maths marks, then in the code for in the pseudocode for passing or calling the create similarity graph, it would have been mentioned. But we are assuming that it is these three values only which I passed directly. But yeah, if we even if we don't assume that, it is still a matrix. Why? Because we are using the keys of that particular matrix for that.
So they are dictionaries, right?
Yeah, they are dictionaries.
Okay.
For that representation, I asked you earlier.
Sorry, can you please repeat? Your voice is not clear if you're speaking.
I asked you earlier for this type of representation actually.
Can you elaborate on that? What kind of representation?
For each ion keys of matrices, right? Max 1.
I'm still not able to understand your question properly. Can you rephrase or repeat the question? Are you there? Okay, I'm not sure if I'm clearly audible, right?
Yes.
Yes, ma'am.
Yes, ma'am.
Okay, so if you still have some doubt in this, please do ask. Otherwise, we can move forward. Okay. So here we just have the summary of what we discussed for this particular one. Now coming to okay, so somebody said they have doubts in the practice assignments also. I won't be discussing everything till too in depth for the practice assignments because those are for you to do on your own. But
Can you take the
if
question 2,
okay, just
2, 3, 4, those 2 to 6, I guess. It's a series of questions.
I'll explain the intuition behind it. I'll give you some idea on how to go about it.
I don't want the answer, the
Yeah.
concept, like what is
Okay.
happening.
So here I'll need to first go through the
You can get
questions.
the PDF version because that would be easier for you.
Yes. I'll take the PDF version. Okay.
Yeah, this one only. Yeah.
So consider the following condensed version of the trains data set. So if we are all aware with the trains data set, right?
Just
So
a
this,
second. Let me refer to the question. I'm not sure if this is the question that I wanted to ask. Just give me a moment.
for me, it is this question only which is showing. At least the problem statement is this only.
No, I think for me,
You're referring
the
to week 10. Okay, sorry. This is week
week
10.
9.
Okay. My bad. I
Okay,
had
no
opened week
worries, no
10.
worries. Yeah, it
So
happens.
week
No worries.
9 PA. Okay. Question number 2 here. Okay, click here to download the PDF version. So question number 2 to
Yeah, this
6
one.
you were saying. So we have this particular table containing the scores of n students. Assume that all scores are between 0 and 100. Okay, the scores in the first and last rows are shown as an example. The actual scores might be different, so refer only to the table's headers to answer all the questions. Okay. So this information is stored in a dictionary S with serial numbers as keys and the corresponding scores as values, similar to what we were discussing in the notations today, right now. A graph is generated from this table in the following manner. Given a pair of students I, j, there is an edge from I to j if and only if i's score is strictly greater than that of j. So first thing to note here is this is a directed graph. We are not saying an edge between I and j, we are saying an edge from I to j. So when we say from I to j, I is referring to the tail of the graph and j is referring to the pointer of that particular graph. Okay, so I haven't exactly discussed that particular thing, but I'm not sure. Can anybody confirm if that was discussed in the previous session or not? Or should I first quickly revise that?
Discussed.
It was discussed, right?
Yes.
Okay. Just a second. Yeah, coming to directed and undirected and directed graph. So when we say a node is there from I, so an edge is there from node I to node j. In that particular case, what we are saying is that if you go back to this scalar draw, right? It's basically this is how we represent it. Let's say this is node I. Rather than I will like to have some general notation here. This is node I. This is P. Then this is how we represent a directed graph. And this is from A to B. Okay. So if there is one particular graph from, let's say, one particular edge from student A to B, then in this case, it is directly said that it represents that I score is strictly greater than that of J. So the graph is represented by a matrix A. Assume that the dictionary S has already been computed. And now study the following pseudocode. So S dictionary was what exactly? The information. 0 gives, in this case,
Serial
for
number
example,
of the
50.
students.
Yeah, the serial number was keys and the values were their scores. So that is already computed. And then we have this particular graph. What is this graph doing? N is the length of keys. So N is basically the number of students in this case.
Number of students.
A is create matrix N by N. A blank matrix gets created. For each R in rows of A. For each C in columns of A. They are simply iterating to the rows in columns. Rows would refer to the outer, I would say, that particular list of students. C columns would refer to the inner, but inner, I mean, the notation, it's not exactly a list, it's the list of keys of that particular dictionary or matrix A. Okay. And if SR is greater than FC, if for that particular row it is greater than SC, then ARC is equal to 1. So from R to C. I score is greater, SR score is strictly greater than SC. So from I to J, there is a edge in that case. So this is simply whatever is written here is represented using a pseudocode. That much is clear?
Yeah.
Now the question asks, a row R of the matrix has 3 entries that are equal to 1 and the rest are 0. Which of the following statements about the student R is true?
What?
A row R of the matrix has 3 entries that are equal to 1 and the rest are 0. This is the question, right?
So
Ma'am, I
there is
think
only
this question
one
is already
student.
discussed.
Sorry?
I think this question is already discussed earlier.
Somebody said that they have a doubt in this question.
I have a doubt. I though it was discussed, but I was on a different call. Hello.
Yeah. Go on with the
Yeah.
doubt.
So if it is one, that means the student has scored more than rest of the students.
If it is one, then again, uh, the row refers to SR, right? SR is greater
Yes.
than SC. Matlab ARC is equal to 1 if R scores greater than C. So if for that particular row 3 entries are equal to 1, that means that particular student has scored more than
Got it. Got it.
clear, right?
Yeah. We can move on to the next question.
Hmm.
Row R of a matrix has 3 entries that are equal.
So again, you can
Again.
try the rest of the questions on your own, and if somebody is saying that this question was already discussed, you can also refer to the recorded meeting.
Okay,
So
fine.
moving on to the other students, do you have any doubts in the questions, or can we move forward to maybe? I think most of the content has been covered only for week 9. So either we can discuss questions, that is one thing, or we can just take up doubts that you have till now in week till week 9.
Hello, ma'am.
The
Yes.
question.
Ma'am, I have doubts in graded assignment week 9.
Graded assignment week 9. Has the deadline passed?
Yes, ma'am.
Okay, then we can take up the doubt. Okay. Share step by step. Yes. What is your doubt?
Ma'am, question 5.
Question number 5. Okay.
Ma'am, 5, 7, 9.
Okay. So question number 5 is based on this particular problem statement. Using the matrix collab computed from the, okay, so we have to refer to the previous problem also. Okay. It's in a very nested fashion, I think. Okay, this refers to 2 questions. And third is for books we are creating, yeah, collab. So the definition of collab is this. So for each I in keys of books, books here represent what? A dictionary. This particular table is represented using a dictionary named books. Keys are serial numbers, values correspond to the list of authors. Okay, assume that books has already been computed, and then books of 0 is the list of the authors. 4 and 0 represent the authors here. And a graph is generated. Each node corresponds to the author. There is an edge between authors I and j if and only if they have collaborated on a book. Again, this is an undirected graph. Okay. Given a pair of authors I comma j with I not equal to j, what does the value collab ij represent at the end of execution of the following pseudocode? So it's pretty intuitive, right? That if they have collaborated on something, then the particular edge for them exists, otherwise it does not exist. Okay, let's go through this one. Collab is create matrix for each I in keys of books. Books, already we know books is this particular list. Sorry, books of that particular author is the sorry, books for that particular book. Serial number is the list of authors that have gone through it. Auth 1 is first of books of I. Books of I means that for that particular book, who is the first author that has, I mean, the first person, author 1. And auth 2 is basically last of books of I, which means the author N. But in this case, it is only 2 authors. Why? Because it has been specified. So this column does not move further to author 3 or author 4, we only have author 2 here. So both these authors are represented using auth 1 and auth 2, using first and last. Got it? That part is clear, how we are deriving the authors from this particular thing. So we had a particular list here in books of I. Now we have that particular author code only. And then collab auth 1, auth 2 basically is 1 if they have collaborated on something. And this is not just a 0-1 graph, we are doing +1 here. So if those authors have collaborated on something, some other book also together, then that particular edge will represent that count of the number of books that they have collaborated on. So what does it represent? What of these options do you think is true there?
Option B, it represents the number of books in which authors I and J have collaborated.
Yes, exactly. So this part is clear?
Yes.
What other questions did you have doubts in?
Question 5.
Yes, this was basically how collab was generated. Now coming to the statement for 4 to 11 questions. Using that particular matrix collab computed from the previous problem, answer the following questions. For each question, what do the variables a-var and b-var represent at the end of the execution of the pseudocode? Pick the correct options. Answers are this and options are this. Okay. Maximum number of collaborators among all authors. What is the correct option for variable b-var? Okay. So this is basically the code for that. A-var is 0, B-var is a list. So firstly, from this, it can be something sort of which sort of represents a particular list, right?
Yes,
that much is clear that okay, this is a number, B-var is a list. Now for each R and rows of collab, so collab was a particular dictionary which shows the number of books that particular R and C have collaborated on. If collab RC is greater than A-var, some number A-var, which in this case is 0, which means that whether they have collaborated on some book or not, then A-var is equal to collab RC. It represents the number of books they have collaborated on. And B-var is now that particular list of R, C, which is those particular authors which are there. Okay, now but this is happening for each R and C in collab. So for some other list of authors, we will again see something. But at the end, B-var is always getting updated and it is not getting appended, right? So B-var is simply a list. But what does that list contain?
Names of authors who collaborated.
Names of authors, yes, but then collaborated on which particular book?
The most often book, ma'am.
Yes, exactly. Why? Because this condition is there. Collab RC is greater than A-var. A-var is right now holding what? The maximum number of books. The answer for A-var was what? What is the correct option for A-var? A-var is the maximum number of books published by
any pair of authors.
No. No, maximum number of books published by any pair of authors, right?
Yes.
Correct?
Yes, ma'am.
So what does that option refer to? Option number 5. So answer for that is 5. But now what would 5 represent given that we know what A-var is? It's firstly it's a pair of authors, right? We have two authors. Why? Because always R, C is there. We are not appending anything. It's not RC or further pairs of RCs, right? It's one pair. So a pair of authors who have collaborated most often would be the correct answer. Correct? For that particular pair, RC, if AVAR is already some maximum number, then RC have collaborated on most number of books together, right? So a
Yes,
pair of
ma'am.
authors who have collaborated most often is the answer. Fifth is clear.
Yes, ma'am.
Now coming to sixth and seventh, again same thing, AVAR, BVAR. Would you like to try this on your own once, or do you want me to go through it?
Ma'am, I have tried it, but I didn't get.
Okay, so what do you think is happening in the pseudocode? Just run me through the pseudocode once.
A var is 0 and B var is 0. That means that is number, some
Okay.
number.
Okay, we have
Then count.
initialized 0. Got
Yeah,
it.
count. We initialize count as 0. Then for each C in column collab, if collab RC is greater than 0, that means the authors, a pair of authors who have collaborated on some books, then count, we increase the count plus 1.
For what? Count is for each R in rows, right?
For each R in rows, yes.
Yes. So we are referring to author R here. For that particular R author, we increase that particular count.
Yes.
Okay. Next.
Next, if count is greater than A var, then A var becomes the count equals to count, and B var equals to R.
So
So
B var
I'm not
represents
getting
what?
this one. B var equals to R. What does it mean?
R refers to the author, right? So B var is the
Yes,
author.
author. Oh, acha. B var is author and A var is how
A var is the count of that particular
count
author. That
of
okay, how many times that particular author has collaborated with any other author.
yes, yes.
Okay, initially we were working with a pair. Here we are working only with one author and any number of collaborations. Could be with multiple authors also.
Okay.
Clear?
Madam, what does that line do? That if that line, this if collab RC greater than 0.
That this is basically checking if R and C have collaborated on any number of books, like greater than 0. So it would be 0 if they have not collaborated at all. It would be 1 if they have collaborated on one book, and subsequently it would be a greater number if they have collaborated on n number of books. In this case, we are just checking have they collaborated or not. If they have, then increase the count.
So that means every time if they collaborated more than once, then count will be incremented.
No. Between R and C, we are checking only once.
No. R because R is the row, and C is the column. So R will compare for each column, means in a row if there is five columns. So each column means and each column also represents some different author. Correct. So suppose R value is 0. So first it will check 0 0. Then it will check 0 1. So if the 0 1 is greater than 0, means if they are collaborated, then count will increase 1. Then it will check 0 2. Suppose 0 2 is there is no relation, so it will not increment it. What?
What happened?
Sorry, my network got disconnected. Am I audible?
Yes, ma'am.
Yes,
Yes.
ma'am.
Okay, sorry about that. Let me just share my tab again. Is it visible?
Yes, ma'am.
Yes, ma'am.
Yeah. So what I was saying was, what last thing did you hear?
Yes, madam. I am just clarifying this thing, this collab RC. So collab RC is comparing each row with each column. So,
No, I mean, yeah, at one time it is comparing that particular author R with all other authors C which are present in the collab.
with all other author, correct. So first, suppose there are 4 author. So first R value might be 0. So it will the first compare 0 0. Then 0 0 is 0. Then goes to 0 1. 0 1 might be 1. Then 0 2 might be there is no relation. Then 0 3 might be one relation. So they can, if there is relation, then value is greater than 0. Then the count value also increment. First it will
Yes.
increment for 0 0 1 and then will increment for 0 3 also. So count value now goes to 2.
Yes.
Right?
Yeah.
So subsequently it will give do this for each other row also.
Yeah, each other row also it will do, yes. So the thing to note here is this whole thing will run for each row. So you are not losing that count anywhere. Count is initialized to 0 for each row, a blank slate for each row. Then we check that particular author R, how many authors has he collaborated with? Has he collaborated with a particular author? If yes, then count will increase. Now we don't care here how many times he has collaborated with that particular author. It could be that with author A he has collaborated 2 times, with author C he has collaborated, let's say 10 times, with the other authors he has not collaborated. We just want to check how many times with any author, not adding it. So the answer here won't be 12 or something. It would just be 2. Has he collaborated or not? It's a binary. Whether he has collaborated, if so, then it is I, then it is 1, otherwise it is 0. Got it?
Excuse me, ma'am.
And then for that particular count value only, we are comparing it with AVAR and then incrementing AVAR and BVAR accordingly. And then we move on to the second row in R, or the first, depending on the index, the R will be 1 then. And then for that R equal to 1, we will calculate count again.
That means, madam, if in uh, in each row, in any row, there is any collaboration, the BVAR value will be the author or name. First,
yes.
The author name represented by the row, that
Yes.
author name will be the BVAR value. If there are at least one collaboration.
Yeah, exactly. No, not exactly, at least one. If count is greater than AVAR, AVAR here already represents the collaborations of the previous R. So it should be greater than that, not for everyone. For the first one, it will increment to BVAR is equal to that author. Then for the second case, it will check that for this new author, are the number of people he is collaborating with more than the one for the previous one? If yes, only then BVAR will include the name of that particular.
AVAR value is not reinitialized. So it is supposed to next time the count value should be more than the previous value of AVAR.
Yes, exactly.
Yeah. Okay. Oh, got it.
So any other doubt? So how many of you, so till now, I think since GA for week 9 has passed, you might have gone through the week 9 contents already on your own also, right? So how many of you are clear with everything that is there in week 9? No doubts. Anybody? Nobody has any doubts? Guys, am I audible?
Yeah, madam.
Yes,
Yes, you
ma'am.
are audible
So
now.
everything is clear in week 9. Nobody has any doubts. What is directed, what is undirected, everybody is clear with everything.
Uh, kind of yes, ma'am. Like I'm just here for revision.
Yes,
Okay.
maybe.
In a directed graph, can we have bidirectional relationships also?
Yes.
Yes.
Okay. So do you we already we have half an hour left, so you have a few options. Either we can drop off. I can take up doubts if you have any doubts till week 9, even if in previous weeks you have any doubts, and or we can start with. I'm not sure if it's so I think you already have one more session for week 9, so I don't know how exactly it would go, but I can start with the representation of adjacency matrix.
Yes, ma'am.
So would you guys like to? Would everybody would be comfortable in starting with the adjacency matrices?
Yes, ma'am.
Okay. So week 9 was pretty basic in that sense. Now, given that we have a graph, what does an adjacency matrix represent? So intuitively, I would say you all have already done it. This is a matrix, and it was right now it was representing 0 0 0 1 0 2, which is the row column pair. Whether this row column here I was doing do something with my matrix ij, right? If I simply increment the count, whether that edge is present, if I increment the count to 1, if that edge is not present, I increment it to, I let it be 0. In that case, it becomes a adjacency matrix. That is all there is to it. So let me just show it this way. Okay. If I have to convert this into an adjacency matrix, right? This was the matrix I had. If suppose I have an edge, so if I have ones and zeros here, first of all, assuming that it is not weighted, okay, let's say here I have 0, 1 and 1. Here I have 1, 1, 1. Let's say I have this random thing. We will try that firstly whether it's possible or not, and if so, we will try to convert this into a graph. Okay, so nodes I have, let's say I have nodes 0, 1. Let me create a few nodes. Okay, this is 0, 1. 0th, basically this particular element, first element that is there. Or okay, rather than that, let me keep it. So if a 3 by 3 adjacency matrix is given, how many nodes will be there?
9.
9 nodes will be there. Who thinks 9 nodes will be there? How many of you think 9 nodes will be there?
Will it be 3?
So how many of you say 9? How many of you say 3? How many of you say some other number?
27, ma'am.
27 nodes will be there. Why?
Uh, all of them will have 2 arrows, right?
No. Okay, all of them will have 2 arrows. That is not how things are being represented. So I and j, when I talk about here, rows are 0 1 2, columns are 0 1 2. Essentially rows and columns are representing the same thing in the matrix, right?
Mm-hmm.
The relation between 0 and 0, 0 and 1, 0 and 2, then the relation between 1 and 0, 1 1 1 2. But essentially everything is the same here, right?
Yeah.
So we will just have 3 particular nodes. And a 3 by 3 matrix, basically an n by n matrix, represents n nodes. Okay.
Okay.
And given the example that I have chosen here, now we will try to populate that, okay, how many edges will be there. So first of all, how many edges will be there?
2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2
6 edges.
How many of you say 6?
Yes, ma'am, 6.
Okay.
6, ma'am.
And do you think this is a directed or an undirected graph?
It's undirected.
Undirected.
Okay. Why do you think it is an undirected graph?
If a matrix is symmetric, then it is directed.
Do you think this is a symmetric matrix?
No, it is not symmetric.
So if it is symmetric, then it is undirected or directed? What is directed here basically? Directed means that
There's only one way to go to the other
no,
node.
directed does not mean there is only one way. So I mean, okay, in one sense you can say that. So if I make this particular thing here, does that represent directed or undirected?
It's undirected graph.
It's
It's
undirected.
undirected. When undirected is there, we can go from 0 to 1. We can also go from 1 to 0, right?
Hmm.
And that is the
Yes,
case
ma'am.
where you are saying that the matrix is symmetric. So symmetric represents undirected. But when I have directed, which means I could have 0 to 1, but I might not have 1 to 0. In that case, it is directed, right? We are directing that, okay, two-way is not possible. We will define what is possible and what is not possible. Correct? So in this case, 0 comma 0 is 1. Do you think that makes sense? Anybody?
No.
No, right? So one thing about adjacency matrices is, unless there is some exception that okay, that our problem statement is defined in such a way that a node can direct to itself, unless that is there, these will always be 0. So this is important. This will always be 0. Why? Because in a general setting, I mean, I'm not saying that examples are impossible of a node referring to itself. It is definitely possible, but at least for the example, so the initial example that I want to introduce to you guys, no node will be referring to itself. Okay. So the diagonal will always be 0 in an adjacency matrix, at least the.
Ma'am, your voice.
Ma'am, your voice is back.
Is it better now?
No,
No.
Okay. Is it better now?
it's
No,
actually
ma'am.
worse.
I think, ma'am, actually worse. What is the issue with the internet or with my Yes.
It's not your internet, probably your mic is not working properly.
Let me try to connect once. Am I audible now?
Yes, ma'am. Now it's
Yes,
somewhat
ma'am.
better.
Sorry? You are
And
audible.
now, yes, ma'am.
Okay, we can continue. So, yes, so what part did you last hear properly?
When the node cannot be directed to itself, it says stays 0, 0, 0.
Yeah, so based on this particular matrix that I have made, now let's try that from 0, do we have any particular node originating? No, right? All of them are 0. This is 0, this is 0, this is 0. I comma j 0, 0, 0, 1, 0, 2. So from 0 to 0 also there is no connection. From 0 to 1 also there is no connection. From 0 to 2 also there is no connection. Coming to the first row, from 1 to 2 I see a connection there.
Yes, ma'am.
So this is one way to represent. Then from 2, how many do I have? From 2 to 1, I have.
Why it can't be in a reverse manner?
Sorry.
The first arrow, it can be also on the reverse side.
Yeah, but I have represented that using another one, right?
Okay.
So here you could have something like this. Okay. This is the representation of this particular adjacency matrix. So this adjacency matrix represents this graph. It is directed. And since it is directed, the matrix is not symmetric. Okay. Got it?
Ma'am,
If
could you please
yes,
explain it once again, but in a layman terms, because
yeah, sure. So here you were clear with this particular matrix, right?
yeah.
So this matrix was representing 0, 0, 0, 1, 0, 2.
Mm.
That is the row comma column.
Yeah.
So 0, 0 represents the relationship between row 0 and column 0.
Column 0.
And now typically when we talk about graphs, rows and columns are representing the same thing only, right?
Yeah.
So we have student 0, student 1, student 2 as rows, and we are mapping the connection with the exact same database only, right? So let's say I had student 0, then I have student 1, then I have student 2, then I have student 3. 4 students I have. Now, if I want to map or compare this, we are comparing it with the same data set. So here also I will have student 1, I will have student 2, I will have student 3, I will have student 4.
Okay.
Okay, now whether this particular student 0 has a connection with any other student, based on that particular row and column I will do 1. But student 0, 0, the notion of connection of this particular, I would say, okay, let me see if I can put it, yeah, this particular thing which will be there, right?
Yeah, it will not be connecting to itself.
It will not be connecting to itself given in a general scenario. I'm not saying it's impossible. There might be some way, some problem statement where we could do that. Just for the sake of that possibility, I'm saying that it is possible. But based on our particular course, most of the times the diagonal row of that adjacency matrix will be 0 because we are not establishing connection to that particular node itself. So student 0 is not getting connected with student 0. We are comparing student 0 with student 1, 2, and 3. And based on that comparison, whether it's 1 or 0, based on that, we will either make a particular node or we will not. Now, when do we know whether to use a directed node or an undirected node?
Ma'am, 1 minute.
Yeah.
That means we always connect from row to column, right? The directed graphs.
So if suppose if you consider this, right? This is 1 comma 2. So I went for this particular one, I went from 1 to 2. This is 2 comma 0. So for this, I went from 2 to 0. So it is from I to j.
Yes, that's what, from rows to columns.
Yeah, exactly. Rows to columns from I to j.
Understood, ma'am, the exact graph. Thank you.
Okay. Now, what is symmetric, non-symmetric? Symmetric is when, as you might have studied in maths also, so I'm hoping everybody of you has completed maths 1 to understand, because that will give you an intuition to understand matrices much better. But even if you don't remember it or you have not taken this one, let me give you a quick revision for that. Symmetric is basically if along the diagonal, both of these places have a mirror image kind of a thing. So here, if you have one, then here also you will have one. So by definition, if it is if the transpose is equal, right? If the transpose for a matrix is equal to that matrix itself, uh, then it is a symmetric matrix. Got it?
Yes, ma'am.
So S1 here, so S0 S1 should be equal to S1 S0 for I comma j. That is basically what it represents. That for each I comma j, I to j and j to I, if both are one in matrix, and this is for each I comma j, I to j and j to I both are present, then it is a undirected one. Why? Because we don't need to put arrows then that okay, this or this. We can simply say that the connection is both ways. But typically it will be given in the question itself that whether it is a directed one or undirected one, because anyway we can update the adjacency matrix, right? So just because it is symmetric does not necessarily mean that by default the problem statement requires a directed graph. It might just be a coincidence, an undirected graph. It might just be a coincidence that for this particular set of points, all the points were connected to each other in a uh, undirected manner, but the problem statement itself might require a directed graph. So while editing it or while doing some updates, it might change into a directed graph. So refer to the question problem statement for that. Okay. Now, for this particular graph itself, how do I make it symmetric? If I turn this into 1, in that case, and if I give it to you that okay, this is a am I audible?
Yes, you are.
Yes, ma'am, you are.
This is a undirected matrix. If I give it to you already, if I define it to you, in that case we have from 1 to 2 and we have from 0 to 2.
0 to 2.
This will be the graph. Okay.
Yes, ma'am.
So adjacency matrix is clear to everybody. This is a very basic intuition that I have given you. Most probably this will be repeated again once. And by default, okay, adjacency matrices are in week 10, right?
Yes,
Yeah,
ma'am.
so in the week 10 session, probably you will see this again, more or less. But since I think we are already in week 10, I thought, and we had time, so why not go for it?
What is the real life application of this, ma'am?
A real life, yeah, that's a good question. The real life application of adjacency matrices, whenever we have a graph, there are several ways of representing that graph, right? So whenever we are given a graph, we just don't want to look at the graph standalone, right? We need to do some operations on it. So
Mm-hmm.
we need a certain way to represent that particular graph, and then based on that, we can do some operations programmatically on it. We can see a
Okay.
graph and interpret things, but let's say we are talking about some traveling salesman problem, right? That a salesman can go from one place to another in this much time or something. So if we have
Mm-hmm.
to compute the shortest path, we need
Mm-hmm.
some particular data structure to represent our particular graph so that we can find that shortest path.
Okay.
Let's say here I'm defining, if we have zeros and ones, here I'm defining the path to be one only for between two nodes. If a particular node is there, or consider this example itself, consider this to be a city. This is city 0, this
Mm-hmm.
is city 1, this is city 2. There is a connection between city 1 and 2, and there is a connection between city 0 and 2. Again, this is bidirectional, of course, because if you can go from 0 to 2, you can go from 2 to 1 also, right? So
Yeah.
some road representation is there, but between 0 and 1 there is no road. So if you have to
Hmm.
go from 0 to 1, you have to go through 2.
Got it.
It means 2 is a host of 0 and 1.
So sorry, if it means 2 is
2 is a host between 0 and 1.
now it depends if is that notation given to you somewhere in the slides. I'll have to check.
Oh, that
I'm
was
not
probably
exactly
that.
aware of this particular notation of being a host.
Oh, that was from the exam, like probably a GA question that he's saying that, because there was a question related to the computer scientist as a host sending out the invites.
Okay, so that is referencing to that particular question itself. It's not a general
Yeah.
notation. Like 2 is
No.
not a general host. So in this
Okay.
case, if I talk about cities, then city 0 to have a connection, city 2 1 has a connection, city 0 1 does not have a connection. Now let's say this is just 3. Let's say there were many more cities, or let me just add one more level of complexity here. Uh, okay. Let's say I add this. 0 can go to 3 and 2 can also go to 3. Okay. Let's say this is there. Now what I want to do is I want to find out the shortest path from 0 to 3. And one more thing, again, distinction. You can have weighted or non-weighted graphs. What are weighted and non-weighted graphs? In non-weighted, everything is 0 or 1, binary. Whether an edge is there or edge is not there. In weighted graph, we assign some value to that edge. let's say 0 to 2, it will take you 3 hours to go from 0 to 2. Okay, from city 0 to city 2, 3 hours it will take. Okay, from 2 to 3, you will take 1 hour. From 1 to 2, let's say you take 2 hours. From 1 to 3, let's say it will take you 4 hours to go. Okay, so the cities are arranged in such a way that, okay, this is how it will go. Let's say somebody wants to travel from 0 to 3. There are many ways to go from 0 to 3. Either it could go to, so firstly it has to go to 2. So 3 hours definitely he or she has to spend, right?
Yeah.
3 plus. After 2, that person has two options. Either it can go to 1 or it can go to 3 directly. Or okay, I want to represent this in that manner. Let's say this is, okay, let's say this is 1 hour. Okay, and let's say this is 4 hours. I want to show that particular case. Now, intuitively here, you see 0 to 2, from 2 to 3, if you were just referencing to zeros and ones, whether we can go or not, in that case, we would have simply gone from 0 to 2 and 2 to 3, right?
Yeah.
And we would have gone there just by binary relation, whether or not we can go. And 2 to 1, 1 to 3 would have been a hassle. That why go to another city when we can directly go from 2 to 3. But in this case, let's say we have a weighted graph and we know that the number of hours that it takes between two cities. In this case, from 2, we have two options. Either we can go to 1 or we can go to 3. So intuitively, I would like to first calculate that from 2 via 1, how much time will it take to go to 3, right? So it will first take 2 hours to go to 1, then it will take 1 hour to go to 3, and this is a total of
6 hours.
6 hours, and directly it would have taken 7 hours.
7 hours.
So here we are calculating and optimizing something, right? That given this graph, there were multiple ways to go from 0 to 3, which is the best way. So in order to do these calculations, we have this representation of an adjacency matrix. There is one more representation, which is an adjacency list. How does that work? In matrix, we just do a binary one, 0 to 1, whether an edge is present or the weight of that particular edge. So in this case, what will the weights be?
Weight is 1.
What will this be? 0 to 2 is 3. 2 to 0 is 3.
2 to 1.
1 to 2 is, okay, so I have, this is now a 4 by 4 graph. Okay, so just forget this one. Okay, let it be. Instead of
create
I'll just
an
create
square
a new
matrix.
one. Yeah, I'll just create a new one. Between 0, 1, 2, 3. Here also I have 0, 1, 2, 3.
Suppose if there is any one more way to go from 0 to 3, then the matrix will work.
Sorry, your voice is not clear. Can you repeat?
If we create that one more way between 0 and 3, then that matrix will be correct.
No, that particular matrix would not have been correct because it's a 3 by 3 matrix. Now for this particular, I want a 4 by 4 matrix. It's 4 nodes here.
Okay.
Okay. Between 0 and 0, nothing is there. 0, 1, nothing is there. So this particular one, instead of writing 0, right, I'll just represent it through a line.
Okay.
Nothing is there. And since it's an undirected graph, I will only fill the upper part of it and assume that it is symmetric accordingly. So 0 to 2, there is something. 0 to 2, we have 3.
It won't be symmetric, I guess.
0,
Sorry?
0 to 2 is 3. 0 to 3 is 0 to 3 is 3 plus 4. 7, na?
No. Here it only represents whether it is there or not. I'm not representing the whole path.
So there
Just
is
the
no
representation of this
Because
graph.
we are
Yeah.
not talking about the total distance. Yeah.
Yes, exactly. We're not talking about the total distance. This part, let me represent it in some other color.
So, madam, adjacency matrices are always symmetric.
No, that is what we were discussing, right? If it is directed, then it is not symmetric. If it is undirected, then it is symmetric. In this case, it is symmetric only because I have chosen the problem statement such that I want it to be directed. Sorry, undirected.
Undirected.
Otherwise, there might have been, for example, in this problem statement itself, right? Let's say there are different modes of transportation. So a train goes only from A to B, it doesn't go back from B to A. In order to go back to B from B to A, you have to take some other route. Then in that case, this same exact thing will become a directed graph. Okay, so it all depends on the problem statement. Between 1 and 2, we have 2 hours.
2 hours.
Between 1 and 3, we have 1 hour. And this is all. Oh no, we have between 2 and 3, we have 4 hours.
3 and 2, 4.
Okay, so this is basically what we have in this particular. Okay, so this is the representation. Only one side I have done, it will be symmetric on the other side also. So here, in order to do the computation for this, we will need this particular matrix. Okay, this is an adjacency matrix. For an adjacency list, what is happening is we write all the connections of that particular node. For example, I'll just give a very naive representation of that list. If I have this right and I have 0, then 0 represents, okay, so 0 would represent, or rather, consider this to be a dictionary maybe. 0 would represent a list of all the connections it has. In this case, 2. Okay. 1 would represent all the connections it has. So in this case, 2 and 3. Then 2 would represent all the connections it has. In this case, 0, 1, and 3. And 3 would represent 1 and 2. So this will be a list notation, adjacency list notation. But we'll see that later. Till now, focus on the matrix. Okay. So on matrix, we can apply different algorithms technically which are there. And based on that, we can calculate whatever we want to. Whether there are nodes between two things or how many are present, what is the best way to go from one particular node to another node. These are some problems. Okay. This much part is clear to everybody. So today I think I'll end here. Time is also 8 o'clock. So time to end the session. And I hope all of this is clear. Even if this adjacency part is not clear to you, don't worry. It's in week 10. It will probably be revised again anyway. So that you can have a quick revision or you can discuss your doubts at that particular point. The other things which are there is degree of a node. So very quickly, 2 minutes are left. I just want to cover that also. When I talk about degree of a node, in this case, right, degree of a node is basically the number of elements in that adjacency list. So 0 is connected to only 1. So 1 degree. 1 is connected to 2, 2 degree. 2 is connected to how many? 3
That
degree.
means number of elements in the list.
Can I ask you, ma'am, what is going on?
Sorry?
Can I ask what is going on? Since I was late.
Okay, so we had covered week 9. We had done most of the revision also. We had discussed most of the things. So there were no doubts in week 9 as far as I asked. So we moved towards week 10 a little bit.
Okay, week 9.
So this is just adjacency matrix I have discussed. What an adjacency matrix is, what is directed, what is undirected, the correspondence of directed and undirected to symmetric and non-symmetric. Then we have weighted and non-weighted. Then I represented this particular problem and this particular graph was there. Why we need adjacency matrices. We also just touched upon what an adjacency list might be, and now I was just telling what a degree is. So degree is basically the number of nodes of one particular node is connected to. So degree of 0 here is 1, degree of 2 is 3, degree of 3 is 2, degree of 1 is 2.
Okay.
That is the notion of
number of elements in the list. Can we say?
Sorry? Number of elements in an adjacency list. So if I consider this adjacency list, right? So here the list itself represents the connections that 0 has. So the number of connections that 0 has is the degree. So the length of this list will be the degree of that particular node.
I have a doubt there.
Yeah.
Since I scored poorly in that quiz too, and what is the that weightage of end term examination? How much it means, 50% or 60%, or how much weightage?
I am not at liberty at sharing the exact weightage right now. Firstly, because I'm not sure whether I can or not. Secondly, I haven't exactly seen the paper, or I don't remember the exact paper anyway. So either ask this again in the revision session for end term. But yeah, what I can say is that the weightage for week 9 to 12 might be a little more as compared to the others. So consider that okay,
Okay.
maybe half the paper should be from the last 4 weeks, and the rest of the the rest half will be from the first 8 weeks in some manner. So,
Okay.
but again, it depends. There is no, I mean, it's not a definite statement from my end. I will have to cross check the paper.
Yeah, yeah, it may be changed. Yeah.
Okay.
Okay.
So this was the notion of degree. Again, in degrees, right? If it's an undirected graph, we have a degree. If it's a directed graph, we have a notion of out degree and in degree. So we can discuss that later. I think
Yeah,
this
ma'am.
is something which is
There is
covering.
one more doubt. In
Yeah.
that our maths 2, stats 2, in that there is a Python subject. There is also a exam for that.
Have you taken a Python?
No, I am asking that in that second term of foundation, there will be a subject. So, is there any particular say, exam?
Exam as in I'm not able to understand. So there'll be quizzes for all the subjects, right? I mean, different subjects can
No,
have different types of
uh,
quizzes or number of quizzes, but yeah,
no. In that term second, there will be an end term examination. So, in that end term examination, Python also included.
it depends on the number of subjects you take, right? If you take a Python, then yes, Python exam will be there. If you don't take a
Suppose that
Python,
I was taking currently I am foundation in first term. I was taken four subjects.
okay. So you will have Maths 1, Stats 1, CT, and English, right?
Yeah, yeah.
So in the second term, it's up to you based on the subjects you pass in the first term. So again, the English 2, Maths 2, Stats 2, and Python, all of them are based on the prerequisites that you pass. So if you pass
Okay,
in CT, then based on that, if you will be eligible for Python, you will have the choice to take up Python, but it's not mandatory for you to take it. It's
okay,
up to
okay.
you how flexible you want to be. So you can take up 2 courses, you can take up 3 courses, you can drop a term also. So that's up to you.
Since I have been tried to complete my foundation in the 2 terms, so that's why.
Yeah, in that case, you'll have to, if you want to complete it in 2 terms, you'll have to take all four: English 2, Maths 2, Stats 2, and Python.
Okay.
So, madam, CT is in the fast term still. Foundation 1. In Foundation 2, there is no CT. So, this is the end of the.
Yes, so CT is computational thinking. Now, based on this computational thinking, we will teach you a language next. That language will be Python.
Yeah, that
So
in
these
that
concepts you
Python.
will apply using Python, and
So there will be a practical examination also in that online proctored mode for Python.
yeah, yes, there will be OPPs also. Again,
Okay.
these are things of the future. Don't worry a lot about all those things. Just focus on clearing the 4 subjects that you have now. Do your best in that. That would be
Okay.
sufficient. You will have enough time to go through the uh, all the contents are also publicly available. You can go through that if you want, and you will also have sufficient time to choose which all subjects you want to take.
Okay.
There'll be orientation for different courses. They will tell you what all is there or not. Attend those meets, and you'll be good to go.
Okay.
Okay, so now I'll stop my screen and I will end the session. Thank you, everybody. I hope all your doubts were cleared. If not, then you always have discourse or the discussion forum. Ask your doubts.
Excuse me, ma'am.
Yes.
Actually, I posted a question on the Discord forum, but nobody has replied, and I also tagged you there.
So, okay, we will look into it. So there were some access issues, I think, with TAs for discussion forum, I think, or discourse. I'll have to check that. But if you have posted, then yes, I'll definitely look into it. Yes. Maybe by Monday.
Actually, I am also facing difficulties in this subject other than the conceptual part, which I already posted there. So, may I ask
Okay.
you?
Right now, it's the end of the session. So I would suggest either take it up in another session or maybe ask it on discourse. But yeah, if you've already posted it on discourse and you want to discuss it in session, then maybe wait for another session. I did ask for doubts till now. In the middle, I did say if you have any doubts till week 1 to 9, you could ask them right now. But I think that particular time, nobody, maybe you were not in the meet at that time. So we continued with week 10. So in the coming forward sessions also, if you feel that you have any doubts, and if the instructor or TA is asking that, okay, we are open for doubts, please do ask them.
What is there what is the CGPA required to become a TA session conductor?
I to be honest, even I don't know right now. You will have to ask this either to the support team. But again, I would urge you all that these are not. So I get these doubts a lot in many of the sessions. What I would urge is don't worry about all these things in the foundation at least. Focus on clearing your basics, and once you are done with all that, then we can think of becoming a TA. So
Okay.
once you're done with CT, go to Python. Even in Python, I would say once you go to the diploma level, do some courses there. I mean, it's up to you based on your CGPA or based on whatever form is floated out. You can fill to be a TA, but I would suggest do some courses first. And once you're clear with the basics, once you have done some diploma courses, then you can think of these opportunities.
Okay. Okay.
Okay. Thank you, everybody. I'll be ending the session. Have a good day.
Okay. Thank you. Anyone is there? Pavan Sharma.